Okay, yes, so let's continue our discussion, or more specifically, examples. Okay, so I will start it with an example. Okay, so we have x1 to xn. Here are all the data points that you collected, and then we assume that the IID follow a normal distribution with the arbitrary mu and the sigma square. Okay. Our goal is to find the MLE of mu and the sigma square, and then also check for unbiasedness, efficiency, and consistency. Okay, so first let's write down the probability density function for normal distribution. So here I use x, so random variable x, and then a semicolon, and I put the parameter mu and the sigma square after the semicolon. And then the probability density function is 1 over 2 pi sigma square. That's the normalizing constant, and then the exponential part, negative 1/2. So here I like to put it's up to you, up to your preference, but for me, because I'm going to take derivative later on, so I would like to put the sigma square here with the 2 on the denominator, okay? But you can write whatever notation that you prefer. Okay, so this is just the density function for random variable x. Okay, so last time we already calculated the MLE for mu, so let me just do it again as a quick summary for that. So here I'm going to write a log joint likelihood, and this one is due to the independency. So you can write from 1 to n and then take it as a product, f of x, and then with the subscript I. Now I'm going to focusing on only the mu, so I'm just going to write mu in after the semicolon. So when I'm working on mu, or when you are working on mu or one of the parameter, you can consider the other one as a constant, so you can consider it as a fixed. And then when you take the products, you will have 2 pi sigma square, and this one has n copies, and then the negative is coming from the denominator, and then the 2 is coming from the square root, okay? And then exponential, and here you have 1 over 2 sigma square, and then summation from 1 to n, and then xi minus the mu, and then you have a square. So this is the joint likelihood. And then for the next step, to get the maximum likelihood estimator, we are going to take the log version to ease our, or to facilitate the computation. Okay, so I'm going to write a lowercase with the parameter mu. This is just the log version of the capital L with the input mu. Okay, and then after taking the log, you will have the negative n over 2, the power, bring it in front of the log, and then 2 pi sigma square, and then minus 1 over 2 sigma square summation, then xi minus mu. Okay, so that is the log of the joint likelihood. Okay, so the log version, a log transformation to the joint likelihood. Then to find the MLE, we are going to take the derivative for our objective function with respect to the parameter of interest, which is mu. And then for the first term, there's nothing involving mu, so the derivative of that would just be equal to 0. And then you will have the derivative for the second term. And then you will have 1 over 2 sigma considered as a constant, and then summation from 1 to n. And then let me bring the 2 in the front, okay? So when you take the derivative with respect to mu, the power will also need to be taken care of. So you have 2 times xi minus a mu, okay? And then you also have additional negative sign, and then I'm going to bring it to the front, so you become a positive term. Or maybe let me write one more step. So you have a negative 1 as a coefficient, and this will give you the positive part. Or if you want, you can also cancel the 2 in the denominator. You will have the following. Okay, so that is the gradient, or the first order derivative. And what should we do next after we have the gradient? You should set it equal to 0, right? And then solve for the parameter of interest. So here we have 1 over sigma square summation 1 to n xi minus a mu. We set this equal to 0. Okay, so we want to solve for an expression for mu. Okay, and then we will have the, so if you multiply the sigma square on both sides, they will be cancelled out. So you will have summation of xi minus n copies of a constant mu and still equal to 0. And this gives you a closed form expression for mu and then hat. Here I'm denoting MLE for the procedure, how we get this estimator. This is the sum from 1 to n xi divided by n. Okay, so you want to find the maximum likelihood estimator for the mu, which is the mean of the normal random variables. Here you have the average of your data point as the estimator. So this is also an intuitive estimator to get your mean for all of your normal random variables. Okay, so that is what we did from last time. Any question or comments? Okay, next let's solve for the MLE for sigma square. Okay, so again I'm going to borrow, or maybe I can rewrite it again. Okay, so now solve for sigma square. And then I'm also, maybe I'll just copy again. So here I'm going to write the log version of the joint likelihood and then focusing on sigma square. So here I put sigma square in the parentheses instead of mu because I want to focusing on sigma square. Okay, and this should have the same formulation. Negative n over 2 log of 2 pi sigma square. Okay, and then let's see, minus a 2 sigma summation 1 to n xi minus a mu square. Okay, so this is the same joint likelihood, the log version of the joint likelihood, but only focusing on sigma square. But this expression stays the same. Okay, once you have the log version of that, you take the derivative of this log likelihood with respect to the parameter of interest. So now we are interested in the sigma square. Okay, so from now on we are going to take the derivative with respect to sigma square, not just sigma. Okay, so we consider the sigma square as a whole. So whenever you work on that, you need to consider sigma square, but not considering the square. when you're taking derivative with respect to that, okay? So now let's take the derivative. So we will have negative n over 2 as the coefficient. And then when you take the derivative of the log, you will have the things inside the parenthesis move to the denominator. Okay, so 1 over that is coming from the derivative of the log. And then you need to apply the chain rule. So the things inside the parenthesis only, and then when you take the derivative, you only have a 2 pi. Okay, now working on the second term. So now we are taking derivative with respect to the sigma square. So everything not involving sigma square should be considered as constant. So this part here will be regarded as a constant multiplied by this thing, okay? So now we have the negative 1/2. So this is also a constant part. And this one is sigma square raised to the power of -1. So when you take the derivative, you will have a factor of -1 sigma square, and this thing raised to the power of -2. And then this one is the constant part. Okay, any question for this part? Okay, so now we have the gradient or the first order derivative. So again, applying the same procedure, set this equal to 0, solve for sigma square. Okay, and we can also simplify a little bit. So we should have, okay, so for example, here the 2 pi will cancel out with this 2 pi, and then we will have negative n over 2 times the sigma square. Okay, so these 2 pi's cancel out. We'll have the n and then 2 and then the sigma square. Okay, so that is the first part. And then plus, so here this negative and this -1 becomes a positive 1/2. And here maybe I'll just add so 1 over 2. And I'm going to put this sigma square as the sigma raised to the power of 4 in the denominator. And then you have this part as the constant. Okay, so this part is just a simplification of this expression here. And then again, set this equal to 0, solve for sigma square. Any question or comments? Okay, so next, just further simplify this expression and then put the sigma square on one side, and then whatever on the right-hand side will be your closed form solution for the MLE. So now multiply by sigma raised to the power of 4 on both sides. Okay, so you have negative n. And also, how about we just multiply 2 times the sigma raised to the power of 4? So the 2 here will also cancel out. Okay. So you have n multiplied by sigma squared plus, so I'm multiplying 2 times the sigma raised to the power of 4, so this denominator just gone. And then you have the summation from 1 to n xi minus a mu raised to the power of 2, again equal to 0. Okay, so then we have the sigma square is equal to the summation of xi. So here I'm going to replace my mu with my maximum likelihood estimator for the mu. So here I'm going to write x bar, which I define this one as x bar. Okay, so this is my maximum likelihood estimator for the mu. Okay, I'm denoting this as x bar, and then when I'm writing my closed form solution for my sigma square hat MLE, I plug in the one that I obtained for the MLE, raised to the power of 2 divided by n. Okay, so that is my maximum likelihood estimator for the sigma square. Any question or comments? So as you can see that your maximum likelihood estimator for the mu can be, let me just say, evaluated from data. Okay, so as long as you have data, you can evaluate it, or you can get a estimation for your mu hat. Okay, so X is all the data, you have n of them, take the average, that is your maximum likelihood estimator for mu. This can be evaluated from data. Similarly, for this one, everything so here everything can come from data, so this one can also be evaluated from data. So as long as you collect data, you are able to get your estimator. Any questions or comments regarding any of the steps?
We are using hat for signifying it as a many.
Sorry, what?
We are using sigma square hat
For what?
for like in the last one line.
Yes, because that's your estimator.
Okay.
Yeah. So here, these are referring to all the unknown part. These are like kind of like the true parameter you want to estimate. This part is the one that you use. You plug in data, you are able to estimate your parameter. So you have a hat. That's your estimation. So that would depending on data. So you collect 1,000 data points, you will have one estimate. You have 10,000 data, you have one estimate. Yeah. So for anything that is estimated by data, you can put a hat on it, just referring that is coming from data. Any other question or comments? Okay, so next, let's check for unbiasedness, and let's work on mu hat first. So checking unbiasedness, we just need to check the expected value for the mu hat if it is equal to the true mu. Okay, so now we want to calculate the expectation of the mu hat, and then we plug in our expression for the mu hat. So this is xi over n. Okay, and then you have the 1 over n as the factor, summation from 1 to n, expectation of the individual xi. So this part is coming from well, you don't need to invoke any of the IID part because expectation is a linear operation. That's why you can just change the order for the summation and the expectation. Okay, and then you have 1 over n, and then n copies, and then each of them follow a normal with mu and sigma square. So the expectation of xi is also equal to mu, and then you will have this equal to mu. So you know that your maximum likelihood estimator for the mu is unbiased, okay? Because the expectation of the mu hat is equal to mu. Okay, now to check for the second one, the efficiency, we would need to construct the Hessian matrix. Well, not the matrix, but the Fisher information, which is related to Hessian. And Hessian is related to the second order derivative of the likelihood. Okay, so again, can I scroll up? Anyone still need the notes? Okay, so now, let me just write down again. This is your log likelihood. So this is not the joint version. Okay, so, okay, so I mean, if you want, or if you want to remind yourself, if you are working on the joint version, if you want, you can also put a subscript of n here. So this is referring to the joint version, okay? You can, if you want, you can also put an n here, referring this is coming from n data point. But here, I'm working, because you want to calculate the Hessian or the Fisher information, this is not the joint version. So if you want, you can also put a 1 here. This is just referring to one particular x, okay? It's just up to you if you want to remind yourself this is the one and that is the joint version. So this is not the joint version, okay? You have 2 pi. Okay, so this is the log for the f of x, the mu, okay? And then the expression is the negative 1/2 log of 2 pi sigma squared. Okay, so you can see that there's no more n showing up here because this is not the joint version. To get the Hessian, you should get the second order derivative from the likelihood only, not the joint version. Okay, and then what is the second part? You will just have the negative 1/2 sigma squared, and then only the x minus the mu. Okay, so there's no more summation because this is not the joint version. Okay, so that is the log likelihood. So not the log joint likelihood. Okay. First order derivative. So dl d mu. So again, the first thing goes to 0, and then you will have negative 1/, sigma squared multiplied by 2 x minus a mu, and then a factor of negative 1. Okay, so let's see if we can simplify that. We will have the 2 cancel out, so and then the negative cancel out. So you have 1/, sigma squared, and then x minus a mu. Okay, so that is your first order derivative for the log likelihood. And here you have 2 different ways to calculate the Fisher information. One of them is that the I theta is coming from the expectation of the score function square. Okay, so that is one way, and the other way is equal to the negative expectation of the Hessian. Okay, so we provided 2 different ways to calculate the Fisher information, so you can use any of them to perform the calculation, and you can choose whichever is easier to calculate. So right now I'm just going to choose the first version. So I'm not going to take a second order derivative. Instead, I'm just going to take a square. Okay, because if you choose the second version, you will need to take another order derivative. Okay, so I don't want to take a derivative, so I will just use the formula 1. But either of them should give you the same answer. So if you try this one, you can try this one on your own later. Okay. So I can also call this the score function for mu. Okay, so here the theta will be equal to mu. And then I'm going to use the first version. I'm going to use this one. Okay, so the expectation, okay, so the left-hand side will be the Fisher information for mu. And then I'm going to use the first formula here, which is the score function squared. So S of sigma squared, and then the expectation of that. We will have the expectation of x minus a mu over sigma squared. Okay, so that is the score function, and then all together raised to the power of 2. Okay, so the score function squared. And then the sigma here is a constant. So when you're working on the expectation, think about what is constant, what is random variable. So here, when you work on expectation, the random variable is referred to x. So the parameter mu and sigma, they all become a constant. Okay. So what I'm trying to say is that here, when you're working on the derivative, second order, first order derivative, Hessian, or those kind of things, you are working on the parameter. So you take derivative with respect to parameter. When you're working on the expectation, everything go back to the random variables. So you should the expectation should be imposed on the random variable x anymore. So we're not working on mu or sigma square anymore, okay? Let's continue, and then we will have 1 over sigma raised to the power of 4 as a constant. So this is the denominator, move it outside. And then you have the expectation of x, and then minus, okay. So I'm going to bring the square thing inside. So x minus a mu raised to the power of 2, and then that is left in the expectation. Okay, so what does the things inside the expectation of x minus mu squared reminds you of? What does that equal to? So we define something equal to that. So what is that referring to? So that is just a definition of the variance, right? So variance is the square of the x deviate from your mean. So this is just the definition of the variance. Okay, so that means you can write it as that multiplied by the variance of x, and the variance of x is just sigma raised to the power of 2, and that is 1 over sigma squared. Any question, comments? Okay, so now we have the Fisher information. Let's get the Cramer-Rao lower bound. So the Cramer-Rao lower bound is equal to 1 over n times the Fisher information. So in our case, 1 over n times the Fisher information for mu. And now let's plug in the things that we calculated. 1 over n times 1 over sigma squared. This is equal to sigma squared over n. Okay, so that is the Cramer-Rao lower bound. Okay, to check the efficiency, we need to check the variance of the mu hat, whether it's equal to this lower bound or not. Okay, so we need to calculate the variance of the mu hat. Okay, any question or comments regarding the Fisher information and the lower bound? Maybe I'll pause a little bit for you to finish the notes. Okay, so we need to verify whether the variance can attain the Cramer-Rao lower bound. Okay, so the variance of mu hat is equal to the variance of the summation from 1 to n xi over n. So that is our maximum likelihood estimator. Okay, so now we move the 1 over n outside the variance. This is 1 over n squared. And then here we have the summation from 1 to n, and then the variance of the individual xi. So here, for this equal sign here, let me just write, this is because IID. You can only do this because they are independent. Otherwise, you cannot bring the summation outside the variance. This is only because of the IID assumption here. Or more specifically, you only need the independent. So you don't. So far, we haven't used the ID part. You only need the first I, and then the ID part is in the second line. Okay. So here, let me be more precise. You have the ID part, the identically distributed part. So you have 1 over n squared, and then you have n copies of that, and then each of them is sigma squared. Each of them is sigma squared. This is because they are identically distributed from the normal, mean mu, and the sigma squared. This is equal to the sigma squared over n. So it attained the Cramer-Rao lower bound. We can also say that this is an efficient estimator. Okay. So if you want, you can also add a comment. It attains the criminal lower bound. So it's efficient estimator. Okay, and then just one more comments. So the variance of the mu hat MLE equal to the sigma square over n, and this thing goes to 0 as n goes to infinity. So you can also make your conclusion this is a consistent estimator. Okay, so we check that the MLE for mu, for the mean, is first of all unbiased, and then we use the criminal lower bound to check that it's efficient, and then as n go to and then as n go to infinity, this go to 0, so this is consistent. Any question or comments here? Yes.
You were checking for efficiency. Could you go up?
Yes.
Could you go up one more line?
Yes.
Could you explain how you got the right side of the very first line?
This one?
Yeah.
Yeah. So let's see. Okay. So this is the log likelihood, and then here let me add a comments here. This is not the joint version. Okay, so it's just the log of the density function, right? Yeah. And then I take a first order derivative of that L with respect to mu, and then I get this one. Do you have any question for this line?
Oh, okay. Wait, never mind. I see why it's.
Okay.
Oops. Sorry.
No, yeah, it's good. Yeah, is that any?
Yeah,
okay,
sorry.
great. Yeah. Yeah, any other question or comments? Okay, if there's no other question, let's work on the sigma square. Do the same thing. Check for all the unbiasedness. So okay, so work on sigma square. So for our estimator for the sigma square, we have this thing here. So now to check whether it's unbiased or not, we need to take the expectation of this expression and check whether it's equal to the sigma square or not. Okay, so now let's focusing on the numerator on this expression here. Okay, and then let's find the expected value for that. Okay, so we need to get the expectation from 1 to n, xi minus x bar. So to work on this, we are also going to apply the same trick that we did on there's a square here. So I'm going to apply the same trick that we did, which is the following. Let me use a square bracket to wrap this one here. And then I'm going to write xi minus a mu, and then I use a parenthesis to wrap them together, minus x bar minus a mu. Okay, and then I'm claiming that this is equal to the left hand side. And the reason and the intuition and what I'm doing here is that I can add it to this equal sign here to explain what I'm doing here. What I'm doing from this to this one is that I'm going to plus and minus the mu inside the square bracket. There's also a square here. Okay. So this is still xi minus x bar, but this is plus mu and minus mu, so it does not alter the quantity here. Any question? So what I'm doing is that inside this square, I'm plus and minus the mu, so it still stay the same, but we have this expansion here. Okay, so now let's continue to expanding these terms here. We will have the expected value, again, summation from 1 to n. And then here you have a minus a b, so you will have a squared minus 2ab plus b squared. Okay, so first of all, you have the summation for a squared. So you have xi minus a mu squared. So that is the summation of a squared. Minus the, so 2ab, and then this b part here, again, it's just a constant, like what we did before. So I'm just going to write 2x bar minus a mu, and then the summation only working on whatever that involving an index I, okay? So this is 2ab and then summation. Because this is a constant, so I can move it in front of the summation, okay? And then plus the summation of b squared. So summation from 1 to n, and then b squared is just the x bar minus a mu, and then square, and then finishing the expectation parenthesis here. Any question or comments here? Okay. So now let's see what else we can simplify this thing. Okay, so maybe we can first work on this part. So let me underline this, the part that I'm working on right now. So this is the n times x bar minus n multiplied by mu. I think we also mentioned this when we introduced the s square, when we apply the same trick. Do I still need any question or comments for when I'm rewriting the part that I underscore here as the following? So you have the summation of xi that is equivalent to n multiplied by x bar, as x bar is equal to summation of xi over n. Here you also minus a mu and then summation of that, so you have n copies of mu, so minus n multiplied by mu. Any question on that? Okay, and then this thing is also equal to, when I bring the n in front, x bar minus a mu. Okay, so the thing that I underscore here is that is equal to n multiplied by that. Any question, comments? Okay. So now, here again, I'm going to change the. Okay, I'm also going to distribute the expectation to each of the three terms. So the first term become the expectation summation from 1 to n xi minus a mu square closing the expectation. Okay. Minus 2 multiplied by n, so this n is coming from here, and then you have 2 copies of x bar minus a mu, so this is equal to x bar minus a mu raised to the power of 2. Any question up to this point? And then for the last term here, I also distribute the expectation, so this one should also be rapid with the expectation. Okay, so I'm doing two things altogether. So first of all is that I'm making this as 2n and then 2 copies of x bar minus a mu, and then I'm also distributing the expectation to the a square, to ab, and then to the b square. Okay, so I'm doing two things altogether now. Okay, and then finally plus the expectation of the b squared term. And here, the b squared term here, x bar is also fixed, a constant, and then, well, I should say fixed, and then mu is also fixed, so that this is just the expectation of n copies of that. There's a square. So the summation of a fixed term is just n times that fixed term, okay? So there's no terms that involve index I, so just n times this part here. Any question or comments? Okay, so here by looking at the last two terms, here you are essentially minusing 2 copies of this thing. If you bring the n inside the square bracket, then you will get the same thing here. So you are minusing 2 copies of that and then adding 1 copies of that. So you only left with a minus 1 copy of that. So that means these will equal to the following. So you only minus 1 copy of them. So you minus 2 copy and then adding 1 copy, that is equivalent to minus 1 copy of that. Okay, so now let's further expanding this. We have the summation from 1 to n and then the expectation. So now I'm changing the summation and the expectation again. You have the xi minus a mu. Okay, you have the n times the expectation of x bar minus a mu taking a square. Okay, so now let me ask you, what is the things inside the first expectation here? What does that equal to? We just actually use that on the, yes?
Wasn't that the variance?
Yes, it's just the variance, right? So the expectation of the random variable deviate from your mean and taking the square, that is just the variance. Okay, and then you have the summation from 1 over n, that is just n times the variance. Okay, so we actually just use this part on the top. So you have n copies. This is coming from the summation. This is coming from the variance. Okay. Also, we have a n, and what does this equal to? What is the expectation of x bar minus mu? Deviate from mean mu and then taking the square. How do we recognize that? There's also the variance, but the variance is for x bar, okay? So x bar also following a normal distribution with mean mu and the variance sigma square over n. So if you still remember this result here, so this thing is equal to the variance of x bar, and the variance of x bar is equal to sigma square over n. So this part here. So you will have n minus a 1 sigma square. Okay, any question up to this point? Yes.
I guess why the difference between like the x and the x bar,
Sorry, can I say that again?
like the x subset I and the x bar, like why the difference between them for the variance?
Can you repeat your question again?
Why the difference between them for the variances?
You mean why?
Yeah.
Okay, sure. Yeah. So here, let's go back to the beginning when we state the question. So so each of the xi following that, right?
Mm-hmm.
Yeah. So xi having the variance of sigma square. Do you agree with that, right? So your question is focusing why the variance of x bar is this one.
Mm-hmm.
Okay. So summation of xi over n. I think back then when we derived this, we have the 1 over n and then one transpose. So vector of 1 multiplied by vector x. That's one way that we rewrite this. And here I'm claiming this as my vector or matrix of A multiplied by x. So this is a linear transformation of x. And then from result 1, when we work on the normal random variables, we were saying a linear transformation of a normal random variable also follow a normal distribution, if you still remember that. So that is the normal distribution part. And then we just need to figure out what is the variance. So now we just need to figure out what is the expectation and variance of that. So let me just quickly adding. No, let's just focusing on variance since your question is variance of that. So we're interested in the variance of xi over n. You have 1 over n squared variance summation of xi, right? And then here, because they are independent, you have 1 over n squared multiply by n of the variance of x. And this is equal to sigma square over n. So this is the sigma square that I put it in here, sigma square over n, and then also the sigma square over n here for x bar. So does that answer your question?
Yeah, I just
Yeah.
forgot about that.
Yeah. So the idea, so first of all is that x bar, which is sum of xi over n, is a linear transformation of a normal random variable. So first of all, x bar should also follow normal distribution, right? That's one result. And the other thing is that the variance of x bar, which is the variance of summation of xi over n, equal to sigma square over n. So that's why the variance of x. So okay, so let me make it. So x itself follow a normal with mean mu and the variance sigma square. X bar follow also a normal distribution with mean mu, but variance is sigma square over n. Yeah.
Could you scroll up like a little bit?
Yeah. Scroll up. Yeah. This part.
Okay, thank you.
Any question, comments? Can I scroll down now? Okay, yeah. Any question?
I had a quick question. Is there a difference, like on that line specifically?
Which line?
On screen, the one with the 3 E's, like the
Yeah, this one? Uh-huh.
Yeah, that one.
Yeah.
Is there a difference if the n is outside of the expectation versus inside the expectation?
This is a constant part, so you can either put whatever you want outside or inside. They are essentially the same. You can put this one back if you want. You can put this one outside if you want. So they're the same.
Okay.
Yeah. So that's why this is minus 2n copies. This is plus n copies. So this is only minus n copies if you want. But here I'm saying this is minus 2 copy of the expectation of n that thing. Then this is adding 1 copy of that thing. Yeah. So n can be moved inside or outside. The thing that you cannot move around is the x, the random variable part. Yeah. Question? Yeah.
For the line above that one,
Yeah.
could you explain again how the first part of where you underline this n times x
You mean the underlying part to this part?
Yeah.
Sure. Yeah. So now let's just focusing on this part. So the summation from I to n xi minus a mu, and then I'm claiming that this is equal to n multiplied by x bar minus a mu. So your question is how from the left to the right, right? Yeah. So now let's take a look on the left-hand side. So this is a summation of a difference. So I'm going to I can write it as the summation of xi minus a summation from 1 to n mod of mu. Do you agree with that? Yeah. So now, for this one here, note that x bar is equal to summation of xi over n. So summation of xi is equal to n multiplied by x bar, right? So the first term here, I make it n multiplied by x bar. The second part here, mu is a fixed term, so I have n copies of that, so I have n copies of mu. So n multiplied by mu, right? Does that answer your question?
Yeah.
Completely?
Yeah.
Okay, good, yeah. Any other question, comments? Yes?
Another quick question, can you move mu outside of the expectation, or does it have to stay inside as well with x?
So, yeah, the bottom line here, oh, can I scroll up, or?
Yeah.
Okay, okay. So, your question refers to what will be affected by the expectation. So the bottom line is that whatever involving x, the random variable part, will be affected by expectation. So only the x should not be moved around or move inside, outside, or like randomly inside or outside the expectation. So for whatever that is not random variable, so for example, you were asking mu. Mu here is regarding as a fixed term. So that will be okay to move it outside or inside. Yeah. Only the random variable part, or the terms involving random variable, you cannot move it outside. So anything involving x cannot be randomly or trivially moving inside or outside. It should stay in the expectation.
Just x only.
Random variable.
Random variable.
Whatever is random. Yeah. Any other question or comments? Okay, so I'm going to clean up the notes. Is that okay if I erase the sketch? Okay, so next, let's continue our discussion on the unbiasedness for sigma square. We haven't showed that it's unbiased or not. Okay, so what we show is the expectation of the numerator for your estimator of the sigma square. So now, let's find out the expectation of the sigma square MLE. Okay, this is the expectation of the sigma square, so you can get your copies. So this is what we get on the top. Over n, okay? And then what we just did is only on the numerator, and this is equal to 1 over n expectation of this thing. Xi minus x bar. Okay, square. So this is what we did above. Okay, this is what we get. So from above, and we notice that this is 1 over n, and then n minus 1 sigma square. Okay, so that means your expectation of your maximum likelihood estimator for the sigma square is n minus 1 over n multiplied by sigma square. And this is not equal to sigma square, so this is not an unbiased estimator. So let me just write not unbiased. So your maximum likelihood estimator for the sigma square is not an unbiased estimator. Okay? As you can see that it's equal to n minus 1 over n, but it's not equal to 1. Okay, so it's not n over n. So it's not unbiased. So usually when you end up with an unbiased estimator, you will need to correct the bias. Okay, so one way to correct the bias is to define an S square in the following way. 1 over n minus 1 summation from 1 to n xi minus x bar squared. Okay, so this is sometimes called sample variance. The only difference is that you are dividing by n minus 1, so no longer divided by n. Okay, so now if you take the expectation of S squared, you will have the 1 over n minus 1 expectation of the summation of this part, xi minus x bar squared. Okay, now borrowing from the above, you will have this equal to that multiplied by n minus 1 sigma square. This is equal to sigma square. So by dividing this part by n minus 1, you are correcting the bias so that S square is a unbiased estimator. Okay, so sigma square MLE is not an unbiased estimator, but the S square defining it this way here, this is a unbiased estimator for sigma square. Okay, any question or comments? So we have this one as the unbiased for sigma square. So by dividing by n minus 1, you are able to correct the bias, and then you are able, so this is an unbiased estimator. Any question, comments? Okay, next, let's check. So we know that S square is unbiased. Let's check whether this S square is efficient and consistent or not. Okay, so that is what we're going to do next. Do you guys need a break? Okay, so let's come back in 5 minutes. earlier someone was asking me if I going to teach the same course next quarter. Is it? Did you ask me that?
Yeah.
Oh, can I ask why is or why do you want? Or I know who is teaching now. I remember that.
Oh,
Yeah.
yeah. I just have a friend who
Next year, right?
had
Who-
to take it.
Yeah. It will be our department chair.
Oh.
I just remembered that because I was also looking who is teaching this class. I just yeah, it will be our chair. Yeah. So I remember who will be teaching, but I'm not teaching it. Yeah, for this one next year. Yeah. And some of you are also graduating, right? Anyone graduating this quarter? Oh, congratulations, you guys. Yeah. So any plan for after graduation or?
Grad school.
Oh, okay, great. Yeah. Also stats.
Bioinformatics.
Bioinformatics. Oh, for it depends. I mean, I know some of the department they have. Some of the bio department they have a more intensive math than stats department. Yes, so I know UCLA for stats bio stats, their stats program is stronger than this. I mean their stats part is more stronger than the stats part in the stats department. And also I know Princeton for sociology they also have very strong mathematical intensity in their sociology. Department. Yeah. You're also graduating? Any plan?
I'll be in grad school here.
Here.
Yeah.
What major?
Natural language processing.
Sorry, what? Oh, the NLP. Great. Yeah. Any other? You also graduating? Oh, any plan for you? Yeah. Well, okay. What major?
Also
In stats. Okay, great. Yeah, congratulations to you guys. Yeah, yeah. I mean, oh, it's okay. Maybe it's too. Okay, no. Yeah. I don't want to, or ask too many. But congratulations to you guys. Yeah. Okay, so let's continue. To discuss the efficiency, we also need to find out what is the variance of the S square. And to find out the variance, right now, the question will be what is the distribution of S square, okay? So this might be a little bit tricky. Okay, so let's work on, or let's start from what we know of, which is n minus 1 S square, and then over sigma square. For this one, we already proved that this is a chi-square degree with degree of freedom n minus 1. This is coming from, so if you want to check this distribution, you can check your previous note. We proved using moment-generating function, we find out this is the chi-square degree of freedom n minus 1. Okay? And for this one, we have, and also chi-square is the special case for a gamma distribution with alpha n minus 1 over 2, beta equal to 2. And for the moment generating function, for, let me write it more precisely. Okay, so maybe I will write it here. So for x following a gamma distribution alpha and beta, its moment generating function for random variable x is 1 minus a beta t and then negative alpha. Okay, so this is what this is all the result that we already derived in even before midterm 1. Okay. And this is the n minus 1 s squared over sigma. So this whole thing following a chi-square, or in other words, following a gamma distribution with this alpha and this beta. Okay. So now to find out the distribution, we can again use the moment generating function to solve for that. Okay. So we know the moment generating function of that. Right now, our goal is to find the moment generating function for s squared. Okay. This is our goal here. Okay. So now we started with the moment generating function of this one. So the moment generating function for n minus 1 s squared over sigma squared, a function of t, is equal to 1 minus beta. So in our case, beta is 2, okay? Minus 2t, and then negative alpha. Alpha is n minus 1 over 2, okay? So that is the moment generating function of this thing where we know that I follow a chi-square or a gamma distribution. Okay, so now let me decompose the right hand side as n minus 1 over, let me think about it. Okay, so I'm going to write this one. So sigma square over n minus 1 multiplying by n minus 1 sigma square, s square over sigma square. So this is your, so if you still remember the property for moment generating function, I consider this as my a, this is my x. Okay, so let me just point out what is the property that I'm using here. So back then, when we introduced the moment generating function, we say that ax, so when we scale a random variable, this is equivalent that the moment generating function, but we scale by at. Okay, so this is one of the results that we already proved from before. Okay, so right now I'm using the same thing. I know this is the moment generating function for this whole thing. So this fraction is one random variable, and right now I'm taking a transformation of ax. Okay, so I'm considering this as my a, this is my x, and this will be equal to the moment generating function for n minus 1 s squared sigma squared, and then a multiplied by t. So a is sigma squared over n minus 1, and then multiplied by t. Okay, I'm just applying this result for moment generating function. Okay, so now let me bring in the moment generating function. This is just 1 minus 2t. So this t now become this new t. Okay, so this is sigma squared over n minus 1 multiplied by t, and then raised to the power of negative n minus 1 over 2. Okay, and now let's revisit our transformation for ax. You will notice that when I multiply by a multiplied by x, you will see that on the moment generating function here, this is just the moment generating function for s squared and then t. Okay, so this is the moment generating function for s squared after I multiply by this factor of a. And now by looking at this expression, you can notice that s squared also following a gamma distribution. And we just need to read out what is the new alpha and beta. And then the alpha is the n minus 1 over 2. And then the beta is 2 sigma squared over n minus 1. So now we obtain the distribution for S squared. Any question or comments? Okay, so let me just summarize what we are doing here. We are interested in the distribution of S squared, and we only know that this thing here follow chi-square. So we do not know what is the distribution for S squared. We only know this fraction follow chi-square. And then we are going to use the moment function of this thing to get the moment function for S squared only, okay? So we are going to use this result, AX is equal, the moment function for AX is equal to the moment function of X, but having the T equal to AT. And now I'm considering this is my A, this is my X, and this will be the moment function of that. But one thing is that after you notice I multiply A by X, this thing here reduced to S squared, and this is just the moment function for S squared. Okay. Now we are ready to check whether the S squared is efficient or not. Okay, so we know the distribution is gamma. So now let me ask a question. For a gamma random variable, what is the variance of a gamma random variable for alpha beta? If you still remember. Or can someone look up? Or okay, okay. So my question, or the thing I'm asking is that if X is following a alpha beta, variance of X, you can look up your notes, is equal to alpha beta squared. Okay, I think this is what we show when we introduce the gamma distribution. Okay, so now we are also interested in the variance of S squared, where we know S squared follow a gamma, so alpha beta, the corresponding is n minus 1 over 2, that is your alpha, and then beta is 2 sigma squared over n minus 1, this thing raised to the power of 2. Okay, so the variance of S squared equal to n minus 1 over 2, 4 times sigma raised to the power of 4, n minus 1 squared. And this is equal to 2 sigma raised to the power of 4, n minus 1. So this is the variance of the S squared. Any question? Okay, so now we know the variance of S squared. To check the efficiency, we need to know the Cramer-Rao lower bound for the sigma squared. Okay, so now we are going to derive the Cramer-Rao lower bound. Before we start, any question or comments before we get the Cramer-Rao lower bound? So again, just to remind you, to check whether an estimator is efficient or not, is that the variance of that estimator equal to the Cramer-Rao lower bound. So right now we know the variance of that estimator is this thing here that we just derived. So the next step is that to find the Cramer-Rao lower bound for sigma squared, and then we want to check whether this one equal to Cramer-Rao lower bound. So that will be our goal here. Yes.
So
So because our first distribution was biased, we're now going through and shifting it over to find.
Focusing on S square, focusing on the one that is unbiased. Yeah. So the sigma square MLE is biased. So, and then we introduce the S square, this is unbiased. So right now we're all focusing on this estimator. So we're
And
focusing.
checking if that's efficient and consistent after the fact too.
Yeah, so we're focusing on the efficiency and consistency for S square. So no longer on the sigma MLE. Although sigma is the maximum likelihood, but it's not unbiased. Yeah. So for the checking part, we're all focusing on the S square. Yeah. That's a good question. Yes. Yes.
What does it mean to be biased or unbiased?
Okay, so that is a very good question. So in statistics, we are collecting data to estimating something, right? And for the bias thing is that, for a bias estimator is that when we're collecting lots of data, so even when we're collecting data to estimate that thing, we are not like a, so for example, if you think, I think maybe this is something that, that most of the statistic textbook will show you. So this is the true parameter, and then you don't know, but you want to collect some data from the population to estimate that. So when you focusing on the unbiased estimator, that means based on your random sample, you are very likely to get your point estimate that is closer to this one. So you're very likely to hitting on the true parameter. So this is unbiased case. So for a biased case is that you are very likely to focusing on another point. You are always hitting this point. Also, maybe for example, the variance can be very small, but you are hitting on the wrong. You are not getting on the hitting on the true parameter. So this will be a behavior for biased estimator, and this focusing on here will be an unbiased estimator. So this is the one that you want to estimate. And then you're collecting data from population to estimate this one. But for an unbiased estimator, so no matter how many data that you collect, you are very likely to hit on this region instead of the true one. So this will be a biased case. Your estimator is biased, so you hit on the not the one that you want, and this is the unbiased estimator. And then the randomness is coming from different data set that you collect, and that you will have some randomness there. Yeah, does that answer your question? Real world example would be, okay, the thing is that, for example, like the height of human, or the average mean of human height is about, let's say, 8. Okay, so you collect 1,000 data point from the population. Let's say anywhere in the whole world, you just collect 1,000 data point, and then you use, let's say, summation of xi over n, this estimator. So this will be the sum of 1,000 people over n. If this is a biased estimator, then you probably will get like a, okay, let me add a precise number then. Like let's say 170 or 175 or that kind of thing. You're very likely sometimes to get 160 or 180, but you are not able to hit this number here if it is biased, if your estimator is biased. But this is an unbiased estimator, so you are very likely to get 175, 173, 176, very close to this one. But if you have a biased estimator, you're probably having a 160, 164, 163, you're hitting on this region here. So that means you are not going to hit on this particular true parameter. Although in the nature, you will never know the average of all the human height. You want to collect data to estimate this one. But if your estimator is biased, that means no matter how many data you collect, you're going to hit on 160 or near 160, nearby 160. But you are not going to hit on this number or nearby. Does that answer your question? Yeah. So sometimes you can get 173, 176, like these are due to randomness, like the random in your data set. Then you will have a very good estimate for 175. But your bias estimator, you're going to hit on these regions that is far from the true parameter. So that is the bias part. Yeah. Yeah, that's a very good question. Any other question or comments? Or do we still have time? Or 10 to 55, right? Okay, so I think for the criminal lower bound, I'm not sure if I can finish in 10 minutes. Maybe I will skip on to the next, but you have midterm. Okay, maybe let me speed up a little bit. Criminal lower bound for sigma squared. Okay, what we want is I of sigma squared. Here, I'm going to use the second order derivative, okay? So I'm going to use the negative expectation of the Hessian for sigma squared, okay? So I want to use this one instead of the expectation of the score square, okay? So now, let's go to the Hessian negative expectation of the second order derivative of your likelihood. Question?
Why are we checking for the lower bound of the sigma squared if we were using S squared before? If we found the variance.
S squared is the estimator for sigma squared, right? Yeah, it's the unbiased estimator for sigma squared. We're still trying to estimate the sigma squared. Yeah, but our sigma MLE is not unbiased. So we choose S squared, but we're still, so sigma square MLE and the S square, they are all trying to estimate the sigma square. So to get this one is efficient or not, we want to check the lower bound for sigma square, right? So second order derivative. Well, this may be a little bit abuse on the notation, but let me sigma. I'll just do two times, okay? But maybe this is a little bit abuse on the notation, okay? So 1/2 log of 2 pi. So this is just your score function. This is just your log likelihood. 1/2 sigma square x minus a mu square. So I'm trying to find the second order derivative for your log likelihood, okay? So let's work on first order derivative first. So expectation, that means you only have one derivative, and now let's work on the derivative of that. You should have 1/2. Oh, I think you can just directly borrow from the previous part. So 2 pi sigma square 1/that multiplied by 2 pi. So this is the same thing that we get from above. Sigma square raised to the power of -2 x minus a mu square. Closing the curly bracket, closing the bracket for the expectation. So this line here is just what we get from above, okay? You already have that. Now taking a second order derivative equal to the negative expectation. Okay, so here the 2 pi cancel out, you have a constant 1/2. And then you only have a sigma square with a power of -1, because that's from the denominator. So you have a -1 sigma square raised to the power of -2, okay? Plus 1/2 -2 sigma square raised to the power of -3 x minus a mu, okay?
For the first term, you have to use chain rule and then actually 2 pi.
Which part?
For the first term.
This line or this line?
So on this line, the 2 pi's cancel out, and then they, I said it's cancel out entirely, never mind.
So this one cancel out, right? Yeah. Closing that. Yeah. Okay, so now let's just simplify. We have the negative expectation, 1/2 sigma raised to the power of -4, so the 2 and the -2, plus the 1/2 and this 2 cancel out, but we now have a negative sign here. Sigma raised to the power of negative 6 x minus the mu raised to the power of 2 of that. Okay, so now distributing the expectation, they should again only working on the random variable part. Okay, so the first part is considered as a constant for expectation. So you have negative 1/2 sigma raised to the power of negative 4 minus sigma raised to the power of negative 6 expectation of x minus the mu raised to the power of 2. Any question? Okay, and then the thing inside the for the expectation part, that again is your definition for sigma squared. Okay, so you have 1/2 sigma raised to the power of negative 4 minus sigma that multiplied by sigma squared. So your final answer should be sigma raised to the power of negative 4, but minus 1/2 copy of that. So you're only left with 1/2 copy of sigma raised to the power of negative 4. And to remind you, this is the Fisher information for the sigma square. Okay. Any typo or?
When you go from, let's say the top line to the second top line.
Here?
Distribute the
Expectation.
The negative. Okay.
Perfect. Thank you. This one. It's the plus, right?
Yeah.
Thanks. Yeah, I made typos when I speed up things. Yeah. Any other? So yeah, positive of negative 4 and then minus 1/2 copy as a sigma of negative 4. So there's positive 1/2. Okay, and then you can just use the 1/. We still have time, so let me just do that. So the Kramer-Rao lower bound is equal to 1/n times the Fisher information equal to 1/n times 1/2 sigma raised to the power of negative 4. This should be equal to 2/n sigma raised to the power of 4, right? Yes. So that's your Kramer-Rao lower bound. And let's go back to check the variance. So your variance, variance of S squared is equal to 2 sigma raised to the power of 4 n minus 1, which is not equal to your Kramer-Rao lower bound. So again, not an efficient estimator. Okay, so that's the conclusion here because it's not equal to the Kramer-Rao lower bound. Your Kramer-Rao lower bound is 2 times sigma raised to the power of 4 over n, but this is 2 times sigma raised to the power of 4 over n minus 1. Not equal to that, it's not efficient. But this is a consistent estimator, so variance of S squared goes to 0 as n go to infinity, so this is consistent. Okay, I'll pause here.